just realized that I had not recorded until this point. So I apologize for that. So those who are not in the class will probably miss this initial portion. Okay. So yeah, in case somebody has questions, then I guess they'll have to. Okay, what do I do? Do I just quickly explain it again? Yeah. Okay, let me just do a quick explanation, right? So we were talking about this Muskingum method, which is essentially uh, uh, an approach which is trying to uh, model the storage in a channel reach when a flood passes through it. The storage, we are assuming that it is a combination of prism storage and wedge storage. So this prism storage, if we assume that the prism storage is some kind of a linear function of the flow rate Q, then I can say the S, which is the storage, is simply K times Q. Okay, and then the wedge component of it, I'm incorporating that into the, this wedge is only relevant when the flood comes into the channel. If it's just uniform flow flowing through the channel, there's no wedge. Okay, but if it's a flood that is entering the channel reach, then at one end I have a wedge with a height of, which is represented by I minus Q, and the other end is simply Q because the flood has not yet reached the other end. So I include that term within the storage as KQ, which is the prism storage, plus K into X times I minus Q. So this K is some kind of proportionality coefficient, and this X is basically representing the properties of the wedge, right? If X is 0, there is no wedge. If X is 0.5, the wedge is perfectly triangular. And if it's somewhere in between, it is some kind of whatever other shape. Okay. So, yeah, and I was asking about this proportionality coefficient. What would be the units of this? Somebody said
Time.
K will have units of time. Okay. So, physically, what do you think that means? Physically, what would that mean? It's kind of
Time
representing some.
variant. Time variant constants.
No, it's not a time. I don't think it's a time varying constant. In this case, what it would mean is how long this the. You can think of it this way: that this k kind of represents the time it takes for the flood to pass through this uh, channel reach. Okay, so that's the this k has that kind of physical implication. Okay, anyway, so now we've got to this stage where we've written storage as a function of uh, k time as a combination of the prism storage and the wedge storage, and the way I've incorporated these two is through this expression kq plus kx times I minus q. All right. So now what I'll do is I'll just take one more slide and I will write the storage term. Okay, at times dj and dj plus 1, similar to what I did previously, right? So I'm going to write sj equal to, what will it be, k times. Okay, now one second, I'll just expand this term out over here. Can I not write this with the k coming out common? I can write it like this: s equal to k times xi plus 1 minus x times q. Right? It's fairly simple. I've just taken the k out common, and then I'm writing the I terms together and the q terms together. Right? So I'll have a 1 minus x times q and an x times I. Okay. So that's this. This is simply a simplified way of writing this, the original equation. All right. So now let me come back to this. So I'm going to write this at times uh, j and j plus 1. So it will be x times I times j I of j plus 1 minus x times q of j. Okay. And similarly, I can write s j plus 1 equal to k times x I j plus 1 plus 1 minus x times q j plus 1. Right? This is okay. And as before, we can simply write this Sj plus 1 minus Sj. What is that? That's simply the change of storage uh, in the channel reach between two time steps j and j plus 1, right? So Sj plus 1 minus Sj, if you assemble if you assemble the terms carefully, then you will get. Okay, I think somebody has a question or something. Chat. Sir, why is x restricted to zero point 0.5? You can ask it now so that I don't stop. Anyway. So the question he's asking is, why is x restricted to zero point 0.5? Ah. So if can x be equal to 1? If x is equal to 1, okay, one second. Okay, he'll say his mic is not working. I knew it. Mic is not working. All right, that's fine, no problem. Okay, if x, the reason x cannot be greater than zero point 0.5 is, if x is greater than zero point 0.5, that implies that the impact of the flood has reached the end of the channel reach, right? If x is 0, there is no flood, right? If x is zero point 0.5, then that is the limiting case where the flood has reached the upstream end of the channel reach, and the downstream end has not yet felt the presence of uh, of the flood. Okay, so it's okay. So when if x was greater than zero point 0.5, uh, what would happen if x was greater than zero point 0.5? It's no longer a wedge then, right? Then it assumes that the flood is reaching, into the channel reach. At this point in time, right, when I write this equation, I'm assuming that the flood has just reached the beginning of the channel reach. So therefore, the water level at the beginning of the channel reach is higher, and then it's propagated to the other end. But at the other end, the effect of the flood has not yet been felt. So therefore, x is, that's why the triangle is the limiting case, right? If I go beyond that, then it means that the flood has already reached the other end, right? So if instead of making it a, right, so if it is like this, that is x equal to zero point 0.5. If I say it's something like this, and then I have the prism, then this means if I give you some depth of flow, additional depth of flow at the downstream end as well, that means the effect of the channel is being, sorry, effect of the flood is being felt on the channel. Okay, so that's probably uh, uh, why we limit x to 0.5. Okay,
Sir, this I didn't understand this equation. Is equal
what is
to
that?
k.
Kq plus kx into I minus q.
Seconds.
Okay, so the kq part you understood. The kq part you understood. The prism storage part. No, I need to know exactly where I need to explain it. Is the kq part okay?
Storage is Q is plus plus
Q is the discharge rate.
discharge rate into K.
K is some kind of a proportionality coefficient. Okay, we are assuming that the storage linearly changes with K.
Storage is quantity, na sir?
Which is a quantity, yes.
So okay, K is time and this one will get means like storage is initially the volume of that one, na sir?
Yeah, so you see, when the assuming that the channel is flowing at uniform flow condition, okay, at any instant in time, if I just take a certain length of the channel, there is some water that is in that reach, right? There is a finite amount of water present within a given length of channel. So in that sense, of storage, it's not going to be there forever, okay, or it's not stagnant water. But if it's uniform flow, it's a little easier to understand. So at any given instant in time, there's a certain volume of water that is stored in the channel cross section over a distance. Okay, that is what I refer to as the storage of the channel. So if I increase the flow rate, the water level will increase a little bit. Okay, but it will still remain within the channel. I have to keep increasing the flow rate for the channel to overflow and then begin to inundate or beginning to flood in the surrounding areas. But as long as the flow rate is below a certain value, that whatever flow rate is being passed through the channel has the ability to accommodate that within its own cross section. So that's what I mean by storage. Okay, it's not stored there for a long period of time. It is the ability of the channel to accommodate the flow within itself, within its own cross section.
Okay. That, then I got what is taking. Then
Okay.
this I minus q somewhat disturbing.
I minus is somewhat disturbing. Okay, so if I have uniform flow in the entire channel reach, I'll have Q here and Q here, right? But suppose I have set up a flow where I have some flow rate at the upstream end I, which is greater than Q, and some and the flow rate at the downstream end is still Q because the effect of the flood has not yet reached there, right? The flood moves. It takes time for the flood to move from point A to point B. So if you assume that this length is this reach, this distance along the channel is sufficiently long, then if you take a snapshot of time at this cross section, I have a flow rate of I, and at this cross section downstream, I have a flow rate Q, which is less than I. Okay, so then if I break down the entire volume of storage, right, it will be broken up into the prism storage and the wedge storage. So the prism storage is already K times Q. It's already incorporated in this term. Only the remaining portion of the storage you have to look at, which is I minus Q, right? Because here the Q portion of the storage is already accommodated here. So I is greater than Q. So I minus Q is this remaining portion, this dotted
Got
line.
it. Yes,
Got it?
got it.
All right. Okay, so let's keep going. So Sj plus 1 minus Sj, I'll try to write it without trying to complicate it too much. We'll just write it simply as the difference between these two terms. So it will be K times X I J plus 1 plus 1 minus X Q J plus 1. Yeah, you can take the K out as big overall multiplying factor minus X I J plus 1 minus X Q J. Okay, so the K is the only term that I've taken out all the way out of the entire thing. Okay, so this is one expression that we are getting. Now, if you remember in the previous, in the what is that, the level pool routing method, also we developed a similar equation which looked like this: Sj plus 1 minus Sj equal to Ij plus Ij plus 1 by 2 into delta T minus Qj plus Qj plus 1 by 2 into delta T. This expression is still valid. What is this expression? This expression is simply ds by dt equal to I of t minus q of t. Right? Instead of writing it in the differential form, I'm writing it as the difference notation, central difference or backward difference, that kind of thing. I'm writing it as a uh, forward difference actually, right? I'm writing it in the it's not difference actually. So left hand side is difference. On the right hand side, I've converted it to area under the flow. Okay. So you agree that this equation is valid even for this channel reach, right? Sj plus 1 minus Sj equal to Ij plus Ij plus 1 divided by 2. Okay, maybe this plus is not very clear. Okay, so this portion is the same as the equation that we wrote yesterday. All right. So now you have two equations with the the same terms on both sides. There's Ij plus 1, Qj plus 1 in both the equations. So both of these equations can be equated, right? When you equate them, what are the knowns and what are the unknowns? Okay, so let us say this is equation number 1 and this is equation number 2. If I equate the two and collect the terms together, equating and collecting similar terms. Okay, are you able internet connection is a little bit weak apparently. So are you guys able to hear me? Hello?
We can hear you, sir.
All right, all right. Okay. Yeah, I got a notification that my internet connection is unstable. Okay. Anyway, so what I'm doing is I'm taking these two equations and collecting all the terms, all the like terms on one side. Okay. So what is the unknown in these two equations? I'm getting rid of sj plus 1 and sj, right? Because I'm taking the right hand side of both of these equations and then collecting all the terms on one side. What are the unknowns? Is ij known? There are only four terms.
Yes.
ij plus 1, both of them are known. qj, we'll assume it's known. qj plus 1 is the only unknown. Okay, so if you look at these two equations, I have ij plus 1, I have qj plus 1, I have ij and I have qj. Same thing over here, ij, qj, ij plus 1, qj plus 1. Now qj plus 1 is the only unknown in both of these equations. So if I collect them all on one side, I can write it like this, something like this: qj plus 1 equal to c1 times I j plus 1 plus c2 times I j plus c3 times q j. Okay, now the c1, c2, c3, well, I'll just write out what those are. I thought I had inserted one more slide. I need to insert one more slide. Just a second. Okay, let me just get back to this screen. Okay, so the C1, C2, C3, I'll just write out what those are. You don't have to memorize them. If you can just simply derive it by equating the terms and then finding out the coefficients of each of those terms. So C1, please don't bother memorizing this. Okay, C1 is simply delta T minus 2kx divided by 2k times 1 minus x plus delta T. C2 is delta T plus 2kx divided by 2k to 1 minus x plus delta T. And C3 is, can anybody guess what it might be? The denominator is going to be the same, 2k times 1 minus x plus delta T. Any guesses on what it might be? Okay, maybe I'll give you a clue. I'll give you a clue that C1 plus C2 plus C3, it's a little difficult to guess without the clue. C1 plus C2 plus C3 equal to 1. The sum of the coefficients is equal to 1. Can anybody try now? Hmm.
2k 1 minus
2k 1 minus x. That's all.
minus t.
Minus delta t. Good. Right? So you just look at the denominator and then you just have to figure out how to get that same thing when you sum up all of them. Okay. So C1 plus C2 plus C3 is equal to 1. If you know that, then you can. That's just an incidental thing. Okay. So basically, if you know k and you know x, okay, you just put it into this equation. You get, and you know delta t. You will get these values of C1, C2, C3. Then you simply come to this equation over here and put those corresponding C1, C2, C3 into this expression, and you can solve for qj plus 1. Okay, and as long as you know q at time t equal to 0, if you know q at time t equal to 0, you can solve for the entire time duration, right? Right. Okay, Now, what I'll do is we'll try to solve a simple problem using this approach, and then with that we'll be kind of done with the flood routing aspect. Okay, so let me go to the Excel file. So, so in the morning we looked at the level pool routing. Now we're going to look at the Muskingum method. Okay. So here's the problem statement. Okay, the inflow hydrograph to a river reach is given below. Determine the outflow hydrograph from this reach if k equal to 2.3 hours, x equal to 0.15, and delta t equal to 1 hour. The initial outflow is 85 cubic feet per second, right? So this it's very interesting, right? So you know that at time t equal to 0, the outflow is 85 cubic feet per second. So that's given over here. Then, if this kind of an inflow comes into this channel reach, okay, this is the inflow coming into the channel reach. How will the outflow from the channel reach be? Okay, so you can think of it, as a river which is flowing at a certain rate, and then I have some control structure, maybe a dam or a pier or whatever it is, and which is experiencing some inflows, and then I decide to release uh, uh, some some of that discharge into this river, which is already flowing at some more or less steady rate. Okay, then I introduce this flood into the river. How does the river respond? That is the objective. And depending on how the river responds, I can decide, how to uh, handle the river and so on. Okay, all right. So now the first thing we would do is, so as if you remember correctly, let me just insert that expression over there. So this is the expression that we are qj plus 1 equal to c1 times ij plus 1 plus c2 times ij plus c3 times qj, right? And we've already developed an equation for c1, c2, and c3. So those, I think I was under the impression I had already put those numbers into. Looks like I didn't. Okay, so it looks like I'll have to solve this on the spot. Okay, so let's do it on the spot. So C1, if you put in those numbers, you will get the numerical answer 0.0631, C2 0.3442, and C3 should be, any guesses? Approximately is also fine.
0.6.
Yeah, 0.6. It's 5927. Okay, because C1 plus C2 plus C3 is equal to 1. Okay, so since we have already solved for this at time step j, which is equal to 0, we have to start solving from time step, the next time step, right? So we are interested in this particular time step. So what do we do? How do we solve for it? Assuming that this is the j plus 1th time step, which we are solving for, I need to solve for the flow at this point, at this time step. So if this is qj plus 1, then I need, what do I need? C1, which is this number. Again, you'll notice that I'm going to do this $J $7, which means that cell I will never change. C1 into ij plus 1. So which of these two numbers will be ij plus 1? 93 or 137?
137.
137. Okay. So I put that in, I get some number 8.6, whatever it is. Then C2 times ij. So C2 will be this number. Okay, $J $8 multiplied by, which one is ij? Will be 93. Okay, so 32 point something. And then the next one, last one will be C3 multiplied by QJ, which is 85. Okay, so I put that in, I get the number 50 point whatever. Now what is QJ plus 1? It is simply the summation of these three, right? Sum, you can simply sum these three numbers, you get the flow rate at the j plus 1th time step, which means 1 hour later, the outflow at the end of this channel reach will be 91 CFS. Okay, then you can just simply, because the formulae are all relative to the location, you can simply just copy it all the way down. Oh, wait, did I make a mistake? There you go, I did make a mistake. So you see what happened here. I forgot to put that $J $9. So when I copied it to the next row, it made it J10, and J10 is empty. Okay, yeah. So this is the kind of mistake you should not do. So it's $J $9. Now if I copy it, it'll be fine. All right. So then I can just copy it all the way down. Okay. So of course, all of these 4 or 5 decimal places have no meaning, so I'll just make it 1 decimal place. Why is it not changing? 1 decimal place is more than enough. Okay. So that is the outflow at the end of the channel reach, right? So now if I know the outflow at the end of the channel reach, what is the point of this? What does this allow me to do? Depending on the cross-section area of the channel, if I know how much water will be flowing at the end of the channel reach, I can take appropriate measures. If some people have to be evacuated, then they'll be evacuated, right? So whenever there's a flood coming, you will hear on the news that people in low-lying areas have been evacuated. Why were they evacuated? Because the people who are making the decisions, they were able to predict what will be the flow rate at this point, and then they were able to compute, okay, so if this is the flow rate, then these are the areas that will get flooded, and then it may cause some dangerous situation, so we should evacuate these people, move them to a safer location, and then they will be fine. Okay, so that is the whole idea of this Muskingum method. Okay, it allows you to estimate the way the discharge, the way the flood will propagate through a channel reach, right? So again, if you notice, you will notice something interesting over here. Okay, now here, because we are not assuming that there is any storage within the channel, okay, you will notice, okay, actually there is some storage within the channel. Let's see. If you notice the peak of the inflow, when is the peak of the inflow? Peak of the inflow is over here, 691 CFS at 8 hours, right? So you'll check out the peak in the outflow. The peak is at 641. Okay, 641 versus 691. 691 was the incoming peak, but because the channel was able to accommodate that peak and then transport it across the uh, uh, across the reach, two things happened. One, you were able to bring down that peak from 691 to 641. Okay, because it was not moving like a uniform flow. It is moving in the form of some kind of a prism. Sorry, wedge. It is moving in the form of a wedge. So naturally, the at the downstream end of the channel reach, you may not have the same peak as the inflow hydrograph. And you also notice that the time has been lagged by a couple of hours. The peak inflow happened at 8 hours, but the peak outflow is happening at 10 hours. So you managed to you accomplish two things. One, you managed to reduce the peak. If the peak is reduced, then the area that will get flooded will be reduced, right? So therefore, the impact is lower, and then you also get more time, so that there's more time for planning and so on. Is that okay? Any questions on this? No, this is a very this is the simplest possible way of looking at hydrologic flood routing in a channel. Okay, usually much more sophisticated, like numerical methods are used, which are more sophisticated, which look at the process from some kind of governing equation of fluid motion. Okay, so this one is just looking at it in the form of how storage is moving. Okay, which may not necessarily be, physically it might not be exactly accurate, but it allows you to get to a solution quickly. Right? How much time did it take? Once you know C1, C2, C3, in a matter of seconds, you can estimate what the flow rates will be. But in reality, this kind of a method is probably too simplistic for real situations. You may take a more sophisticated approach. Okay, yeah. So I think with that we are done with the flow routing uh, chapter. We'll look a little bit at floods and things like reliability and risk and so on. When we're looking at precipitation, I remember we did speak a little bit about reliability and risk, did we? Exceedance probability and so on. Did we just spoke about exceedance probability? Huh? Did we speak about risk and reliability?
No, sir.
No. Okay. So then, when it comes to floods, we'll talk about risk and reliability. Okay. So the next class is on Thursday. So on that day, we are going to have the presentations. So on next Monday, we will finish up with floods. We'll look at reliability, risk. We'll look at measuring discharge in a channel and so on. Some small topics, and then we will move on to groundwater. Okay. So from the next week onwards, we'll start talking about groundwater. Okay. So one more class, we'll talk about floods uh, and discharge measurement and so on. After that, we move on to groundwater. So with that, when we finish groundwater, we'll be done with the entire semester. Okay, so we have about 2 more weeks after this week. We have 2 more weeks of classes. All right. Okay. Thank you very much. We will meet on Thursday at 10 o'clock. All right. Take care and see you then.